So far in this chapter, we've looked at how we can make use of differentiation and integration to help us work with problems involving kinematic variables. So our suvat variables: displacement, velocity, acceleration. When we first came across these variables, we learned some formulas that apply to constant acceleration. But recently, we've been looking at instances where acceleration, velocity, displacement all vary according to the time into the journey. So we've been looking at variable acceleration, variable displacement, variable velocity. We now actually want to show that we can still use calculus, and by using calculus, we can derive the formulae that we learned back when we first encountered suvat and suvat variables. To do that, we'll use our usual differentiation and integration techniques, but we need to consider acceleration to be constant. We need to consider that variable itself to be constant. Okay, so let's have a look. Here, we're told that a body has constant acceleration a, its initial velocity is u, and its initial displacement is 0 meters. We've been asked to prove, firstly, that the final velocity, v, equals u plus at. So that's a familiar formula there, but can we generate that for ourselves, starting with variable a? So we know that velocity is going to be acceleration integrated. So if we integrate a, we're going to get at plus c. This constant of integration, I can find its value if I use the information given to us. We were told that the initial velocity is u. We actually knew that. We've always known u to represent initial velocity. More specifically, initial means that the time equals 0. So I can formalize that maybe a little bit by saying that when t equals 0, v equals u. So when time is 0, the current velocity is the initial velocity. Okay, let's actually use that to calculate a value for c. So u is substituted for my v, 0 is substituted for t, and we're left with c. Okay, just tidying that up, we can see that u must be c. This constant is the value u. Okay, let's come back up here and we'll write this equation in its full. V equals at plus the constant we found, u. This looks familiar. Just rearranging the order we've written it. There we go. We've deduced and derived that suvat equation that we love so much. Okay, let's go one step further. If we were to integrate the velocity, what will we get? I hope you're expecting to get displacement. Let's give it a go. So displacement is usually what we get from integrating velocity. We found that velocity is u plus at. So if we integrate with respect to t, u becomes ut. And here we're going to increase the power on t, so it becomes t squared, and divide by that new power. So we're going to have a coefficient of a half. We're going to have a t squared plus a new constant of integration c. Okay, let's see if we can find out what that constant, that unknown constant is. We know, and we were told in the question, that when t equals 0, the displacement was 0. So at the very beginning of the journey, displacement was 0. But that's also a given. That's information we should know all the time for every question. Okay, so let's substitute. Well, displacement is 0. T is going to be 0, so I'm substituting 0 into these first two terms. And we're left with just plus c. Okay, rearranging this, we get that the constant is 0. The constant doesn't equal anything. So coming back up here, we can now fill in our value for the constant. S equals ut plus half at squared plus 0. And there is no real need to write the plus 0, but once again, we've derived one of our familiar suvat equations for constant acceleration. So just starting from that point, where acceleration was just a constant. We described this as a, and then integrating with respect to t, we've managed to derive these two. So there's a number of practice questions for you to use to see if you can work with and derive these standard SUVAT equations through use of calculus.